I shortened the title, cutting out some, it's still the same talk, but exascale simulations of pulsar magnetospheres cut through some of the fluff. So pulsars are extreme physics laboratories. They're some of the most extreme environments in the universe. So they're neutron stars, which are the highly dense remnants of supernovae. They have anywhere from 1 to 2 times the mass of the sun, but are much, much smaller, down to a radius of only 10 kilometers. So to make a pulsar, we can imagine taking the sun with its radius of 700,000 kilometers, and then shrinking it down so it fits between El Cerrito and Oakland. So that's a neutron star. Then to make it a pulsar, we spin it up so that it rotates anywhere between 1 and 1,000 times per second. And pulsars also have magnetic fields 1,000,000 times stronger than anything we've created on Earth. Now, to be clear, we can't actually create a pulsar. And in fact, we can't really even recreate the pulsar environment in a lab. And so the only thing that we really get from pulsars is light. And pulsars emit all kinds of light, ranging anywhere from high frequency radio pulses, which is probably what they're best known for, out to high energy gamma rays. And the high energy gamma rays are particularly interesting because they indicate that pulsars are surrounded by plasma that has very, very energetic particles that are moving at much higher velocities than anything that can be produced from conventional particle acceleration theory. Now, the best way to simulate these kinds of particle interactions and these kinds of plasma instabilities is with particle and cell. So particle and cell is a computational technique that's very commonly used in plasma physics, where the plasma is discretized into particles, which represent bundles of electrons and protons. And then the code, in this case, the cell code warp-X, tracks the particles as they move across this spatial grid where the electric and magnetic fields are calculated. And this allows us to self-consistently evolve both any external and also internally generated fields in the plasma, while also tracking non-thermal particle acceleration, which is the thing that we're particularly interested in studying. But the challenge with doing these kinds of pulsar simulations is that pulsars are 10-kilometer objects surrounded by 100-kilometer features, like this current sheet here in red. But all the plasma instabilities we're interested in happen on centimeter scales or smaller. And that factor of 1,000,000 scale difference isn't something that we can resolve in 3D. So we take a two-pronged approach. The first is to scale down the pulsar simulations, which is the aspect of the campaign that Reva is leading. And then we're also zooming in on the plasma instabilities themselves and doing really detailed studies of the physics. And that's the component that I've been leading. And the idea is that once we have these scaled-down pulsar simulations and these plasma simulations, that we can then use the details of the plasma to feed back into the pulsar simulations and try to connect these very disparate scales. Now, one thing I'll be talking about a lot throughout this talk are these current sheets. So a current sheet in this case is a sheet of current, in this case flowing into the page. And current sheets, the reason why they're important is because they are a site of particle acceleration, and in particular magnetic reconnection, which is one of the processes that's expected to operate around pulsars. So current sheets generate, due to Ampere's law, these anti-aligned magnetic fields. So on the top, the fields are going to your right. On the bottom, they're going to your left. And the field lines are drawn in towards one another, and they drag plasma with them. But as they do so, they reach the center, they can't cross, so they break up, reconnect, and accelerate plasma outwards along the horizontal direction in this case. But the current sheet won't stay in this nice, neat configuration like this animation. Instead, it'll fragment into these structures called plasmoids, which in this case, so it'll structure into these plasmoids, which will travel outwards and merge, and trap plasma as they go. And as if we were to look down on this box, they would look like strings of current running into the page. So I'd like to start the discussion of the results with talking about some of these large lens pulsar simulations. So to do these, we set up some initial condition that represents the fields that surround a pulsar. and then inject electrons and positrons. So the electrons in this movie are going to be in red, the positrons are in blue. And there we go. So the positrons will form in this case, a sort of disk-like structure, and the electrons will form a dome. And this is a quiescent pulsar, so a one with relatively low magnetic field. And the low magnetic field means that there isn't as much particle injection there isn't as much pair production, which we model as particle injection. So we get this disk dome structure, which is a nice validation case, but we don't really see much of a current sheet. In fact, there's no current sheet. And so there isn't much particle acceleration. To achieve to get these current sheet structures, we have to increase the rate of injection, which corresponds to a stronger magnetic field. So this is another one of Reva's simulations, this time with a higher injection rate. So we're starting to see a sheet of current extending outwards. So in this case, electrons in blue and positrons in red. This is showing charge density, showing the sheet starting to form. And then this is a rendering of charge density only showing the positrons in the disk. It sort of looks like a disk, but it's a current sheet in this case. And then we've also been able to verify that there's actual current going on here and it's not just a bunch of charge. So this is showing the current magnitude normal to the surface. So here this is showing current coming out of the flat plane and into the flat plane. And that's just representing the primary direction of the current is moving radially, which is along this direction. But the component that's being shown here is just showing the rotation of the disk. But then the thing that's really cool is that we're able to look at the current that's flowing through the cylinder, which is this radial component. And we can start to see what maybe looks like some plasmoids going on. So this is some hints of reconnection, and we're starting to see these in a number of other global pulsar simulations with other injection rates and rotational configurations. And while there's a lot of rich physics that we can get from this, we're still not able to resolve reconnection at the scales we're interested in. So for that, we use these small N simulations, where the setup is a box that's only 10 by 20 meters in size, which is about the size of the smallest cell in some state-of-the-art pulsar simulations. So we're really, really drilling down into the plasma physics here. So we have a pair of current sheets, one coming out of the page, one going in, and then these anti-parallel magnetic field lines. So as I let this run, we'll see that the current sheets fragmoid into the plasmoid structures that I mentioned before, and the plasmoids will travel outwards and merge until we form a single plasmoid at the edge of the current sheet. And this is just because it's a periodic domain. If there was an outflow boundary condition, the reconnection would continue, and everything would continue to stream outwards. These simulations have 3 billion particles and tens of millions of cells, but only take 1 to 2 hours on 21 Summit GPU nodes because WarpX is highly optimized for high-performance architectures. So one of the things we're looking at doing, which I'll get into in a second, is expanding to 3D because the code can handle it. Another nice way of visualizing this is here. So we have a string, I've labeled some particles in blue that travel into the current sheet as it reconnects, get trapped, and then travel outwards. And this is useful for measuring some of the detailed physics of how exactly reconnection happens, because we could track, say, what are the electric and magnetic fields at each of these particles as a function of time for looking at where the electric fields that cause the energization are being generated. Now, one of the things that I've been harping on a bit is particle acceleration. And so one of the things that's been nice about this is being able to quantify the particle acceleration that happens and match that against the literature, which fortunately it does. So this is a histogram of of particle abundance on the y-axis, velocity or kinetic energy on the x. And as the simulation progresses, the lower energy tail swings outward, indicating that plasma is being accelerated, and we're seeing about a 10x increase in the highest kinetic energies of these particles, which is about what's expected given the parameters of the simulation. So all of that's holding together. Now that we have a good sense of what's going on in the 2D simulations, we're looking to move to 3D. And the current sheet structures that we're seeing here, in the current sheet here, we're starting to see some deformation, which is indicative of a drift kink instability, which is a type of instability that forms in reconnection in 3D. And we're also starting to see that in some pilot 3D simulations here. And so we have a good sense of what's going on now in some baseline pulsar and reconnection simulations. And so now we're really thinking about how can we connect the global and local scales. There's a number of ways we're thinking about doing this. As I mentioned, we're studying 3D instabilities. Our intern Lizette has started working on some mesh refinement testing, which will allow us to do new physics. We're also thinking about ways of coupling in particle and cell simulations in a global magnetohydrodynamics run. So yeah, I'll leave it there, but I've left my email here if there are, if you have any ideas for things that we should try or if anything jumped out to you, and I'm also happy to take any questions.
Let's thank the speaker. Thank you, Hannah. Any questions? You have a question? Yeah.
Yeah, maybe. I will just ask a question. So, could you clarify that is the 3D instability a result of numerical you're using, or it's actually the physical system itself is being stable?
It's actually a physical thing. So the flux ropes will start. So if you imagine like sort of like spaghetti going into the so the flux rope is like spaghetti in 2D. In 3D, because it can start to wiggle and bend around in the Y direction, it'll start folding over itself. So there's an image that I like to show sometimes where like in 2D it's sort of like spaghetti, and in 3D it's like instant ramen, all curled up on itself.
Thank you.
Thank you, Hannah. I'm hungry now. Any other questions? Are there any questions on Zoom? Okay. So then we can start switching the speaker. And thank you again. Thanks, Hannah.